Right, we've talked about it before, we've mentioned it a little bit in this unit, so let's talk about the pendulum. So if we have small displacements from equilibrium, we can absolutely say that a pendulum exhibits simple harmonic motion. So it's absolutely going to go back and forth repetitively, assuming no friction, air resistance, or any other losses. Now, there is an equation here that we're going to present without proof. If you want to derive it, that's fine. But the restoring force for a pendulum is going to be a little bit more complicated. So the restoring force is actually going to be the negative of the force of gravity multiplied by sine of the angle. So if we kind of look at this diagram here, here's our angle, our displacement from equilibrium. So we are certainly going to have our force of gravity acting down. We have this force of gravity perpendicular, and then we have this this F restoring. So that restoring force is going to act pretty much tangential to the displacement. So kind of think of this, the restoring force, almost think of it, it's similar to an inclined plane, almost think of it like the parallel component of the force of gravity. It's the same formula, except for that negative there, because we want that displacement and the force to be in opposite directions. So our restoring force is going to be this negative Fg times sine of theta, or negative mg sine theta, if you so please. The pendulum, we've already talked about it in with conservation of energy. We could talk about it in terms of an oscillator. At the top of its swing, 0 speed, and it's going to have maximum force and acceleration in the opposite direction of the displacement. As it swings down to the bottom, that potential gets converted to kinetic. So at the bottom here, because we're at equilibrium, we're not displaced from it, no restoring force, no acceleration, maximum speed, we'll say in the negative direction because it's traveling right. And then, it's going to go up to its maximum position after it converts all that kinetic to potential. No speed, maximum force, maximum acceleration, and then, we're just going to assume that that repeats over and over and over again. Again, assuming no losses. So for this whole back and forth, so for this pendulum, when it starts here, it oscillates to this side and then comes all the way back. That represents a complete cycle for the pendulum. The time it takes for it to do that, that's going to be the period. All right. Now, we do have to be a little bit careful though. You may have noticed, maybe you didn't, it's fine. You may have noticed I wrote the word small displacement from equilibrium. This is where we have to be a little bit careful with the caveats. And it's a real subtle thing. When we talked about the definition of simple harmonic motion, the definition is that the restoring force is directly proportional to that distance from equilibrium. Or rather, what we have is that F is directly proportional to negative x. For pendulum, you see here, Fr is equal to negative Fg sine theta. The restoring force is proportional to negative sine theta. This is not a linear relationship. Now we might think, uh-oh, what happened? Is this bad? No, it's actually not as bad as we think. Normally, we would say, okay, this is not a linear relationship. We can't say that it's simple harmonic motion. We're going to just do a little bit of magic here. We're going to do a little bit of, we won't even call it lying, but we're going to kind of do a little bit of a restriction. So this whole thing is generally true. In general, pendulums don't exhibit simple harmonic motion, except at small angles. So you see this graph here. This graph is showing force as a function of displacement. So this curve, solid curve, is the actual function. So you'll see it curves. So it's a sine curve. And then this dashed line represents a linear function. Now, over here, it's very clear that these are not even similar. But notice in here, like kind of in this region, the linear function and the sine function, they're almost indistinguishable at these small angles. That is our way to kind of get around this restriction. So we can say that this is simple harmonic motion. What we're going to say is a pendulum does exhibit simple harmonic motion, but we're going to say that the displacement, we're going to say it's less than 15 degrees. So if we say that displacement's less than 15 degrees, its displacement from equilibrium and force have a roughly linear relationship. So we're going to say that that is exhibiting simple harmonic motion. Once we start to exceed that angle, and once we start to get out this region where the sine function and the linear function are very distinguishable, then simple harmonic motion breaks down, and then that's where we have to start doing some more advanced mathematics that we will not be doing in this course.